is Salim Tayou from Harvard University, who is going to talk about the non-abelian Hodge locus.
All right, thank you, Roberto, for the introduction, and thanks, Hussein, for the invitation. It's a pleasure for me to speak here today. Everything that I'm going to talk about is joint work with Philip Engel. And so let me first start with some motivation and historic background. So a classical theorem due to Parshin and Arakilov from the 70s states the following thing. If you fix an integer g bigger than 1 and S a smooth quasi-projective curve, then there are only finitely many families of curves of genus G, which are non-isotrivial. And so this is a family of curves, so smooth projective, up to isomorphism. So this set is finite. For some add-in Parshin and Arakilov, when S is projective, this result would due to Parshin, and then Arakilov generalized this result for any S. Now, this might also remind you of a later result of Faltings, also over C. So everything here is over C. So throughout the talk, everything is over C. Yes. I'm sorry. Oh, yes. So CG, family of curves of genus G. Yes, thank you. Yeah, thanks. No, there's no singular. I mean, I'm somehow S. I don't assume that the S is projective. So this is a Q for quasi-projective. So this family might have singular fibers, but in a prescribed set, which is the compact. The morphism here is smooth projective, yes. So there's a family of curves of genus G, so it's smooth projective. And yeah, so Parshin did it when S itself is projective, so the whole family is you're taking a complete family of smooth curves, like smooth projective curves, and Arakilov generalizes for any S. And so if you compactify S, this amounts to saying you're having a family of S bar with a prescribed set of singular fibers. The singular fibers are only allowed to be in S bar minus S. So Faltings later in the 80s, 83 or something, gave a similar result for abelian varieties, for family of abelian varieties. So here, like the naive statement is not true. If you take like a family of abelian variety and you take the product with an isotrivial family of abelian variety, then you can vary the isotrivial family in an infinitely many way. So you have to be a little bit careful, and so there's like some assumption some necessary assumption that eliminate basically this type of counterexamples. And once you have this assumptions, then let me call them just star for now. Then the family of abelian varieties over S of dimension G and which are non-isotrivial, and that satisfy this mysterious star assumption that I'm not going to detail. It's not important for the talk. Modular isomorphism is also finite. So there are only finitely many family of abelian varieties over like of dimension G over a fixed curve. So this, of course, Faltings later proved some analogous statement over number fields. So one consequence of this result is the following. a family of curves or a family of abelian varieties, by what we saw this week, gives you a polarized variation of host structure of weight 1. So we get a ZPVHS of weight 1 on S. So there's some local system and some filtration and some data of a polarization. And so in particular, this local system here, once you fix a base point in S, it gives you a representation of the fundamental group of S into GLN, or like GL2GZ. In fact, it lands in a smaller group, but it doesn't matter. So this is the monodromy representation. Yeah, let me just land it into a GSP. And the consequence is that there are only finitely many representation of the pi1 into GSP2G or GLN that underlie a ZPVHS of weight 1. So corollary. The set of representation of the pi1 into GL and Z that underlie a ZPVHS of weight 1 up to conjugacy, again, is finite. So this is a weak corollary of this two following statements. And in fact, the proof of these two statements, well, they don't really use exactly this corollary, but the idea of the proof is that in both cases, you can parameterize these families via maps from S to either MG, like the moduli of curves, or AG, the moduli of abelian varieties. So idea of the proof. This is the data of such family is equivalent to data of the period map, so either MG or AG. And what this group of authors do is that they parameterize the set of maps from S to MG or AG and give it an algebraic structure. And plus, they show that the image has bounded volume. So bounded volume, like fixing some projective embedding of MG or AG. And then the last step is a rigidity statement, meaning that any such map does not have any infinitesimal deformations. And so that's what gives you finiteness of the set of such representations. So yeah, so that's the idea of the proof.
But the result of faultings, the principal polarization is priorly hypothesis?
The what, sorry?
The result of faultings, is it principally polarized?
No, in fact, I mean, faultings rated for principally polarized, but by Zarin's trick, you can reduce to like any polarization, and then you can construct out of it a principally polarized. So it's yeah. Okay, so motivated by or intrigued by this result of faultings, Deligne proved the following generalization. If take X, any smooth quasi-projective variety over C, and look at the set of representation of the fundamental group of X at some point in GL and Z that underlie a ZPVHS of any weight, modulo conjugacy, and I prove that in fact the set is finite. So in weight 1, it's a consequence of this, like this result of faultings and Partian-Arakelov, but in higher weights, it requires different arguments. And in fact, Deligne asked the following question. So ask for a uniformity result of this statement. And by this, I mean the following. Let me, for simplicity, assume that x is just a curve. So x and this curve itself moves in some family. Oh, let's call it S, or SZ. So this is a family of curves. And I assume like this is a smooth family. And SZ, I can compactify it in some SZ bar. Now this is a smooth projective family of curves. And the complement of this SZ inside SZ bar is just some finite étale over Z. So I'm taking a family of curves and I remove uniformly some sets of points. And so these are punctured curves. And for each one of them, so each one of them has a pi1 at some point, let's call it Z. For any little point Z in the base, like the curve has a pi1, and this pi1 form a local system on Z. Right? So this is a smooth family. The pi1s, like locally, you can identify the pi1s of the fibers, and then you have an action of the fundamental group of Z on this local, on the pi1 of the fiber. So this is a local system of fundamental groups, Amenhofer groups. And so whenever you're given, let me go to the other word. So whenever you're given two fibers over 2 points Z1 and Z2, so SZ1 and SZ2, any path that links, let's say some point A here to a point B here, allow you to identify the pi1 of SZ1 at A to the pi1 of SZ2 at B. There's some, like some parallel transport for like fundamental groups. And now, Deligne's question asks the following: like this generalization or like a uniform version of this finiteness results. I'm just take any point in SZ1A, I'll call it A, and any point in SZ2, call it B, and take a path in SZ that links A to B. So along this path, you can do this identification. Of course, this identification is up to the pi1 of Z, like up to some mapping class group. But take any identification. Okay. Now, whenever the pi1, so let's call sigma gn the pi1 of a surface, like a Riemann surface. So a curve of genus G with n punctures. So, so whenever you have the pi1 of a surface like this, like a pi1 of a curve, sorry, a Riemann surface or a curve, whenever you have a representation that underlie a PVHS, then you obtain a representation of this abstract surface group via this composition. And Deligne's question now asks, if you look at all the representation of this surface group, psi, into GL and Z, that underlie a Z PVHS on some surface, on some curve on this family, on some SZ. So again, modulo, well, conjugacy and action of the mapping class group, or like of the pi1, and like up to identifications. So this, there's an action of the mapping class group. Then, in fact, this set is finite. So this is a question, Deligne. And up, you know, this question is very general, so you can assume that, in fact, SZ over Z is just the universal family. You don't, you know, it's much more general. So the universal family of curves of genus G with n punctures. So if you fix, of course, if you fix just one variety, then you recover the Deline's theorem. But the tricky part is that as your family moves, like as your family of curves moves in itself in a family, then there might be more and more representations of the pi1 that appear and that underlie a ZPVHS. So actually, Deligne proves that this is true in the shim, like in weight 1, like which is like the abelian variety case, basically by just following arguments of Arakelov and Feltings. And the hardest case is when like higher weights or Shimura varieties which are not of abelian type. Or, I mean, open case, I would say. So this question can be put in a much global setting and maybe a more conceptual setting. And this is through the work of Simpson. So let's say a global version. So before, yeah, so this is like, so this sort of formulation that I'm going to explain now is due to Simpson. And before explaining it, let me just recall quickly the main objects of Simpson work on non-abelian Hodge theory. So if you fix x over c, smooth projective, Simpson introduced several moduli spaces. So there is the Betti space, which Betti space of x, which parameterizes which is a moduli space of a representation of the fundamental group of x into GL and C, let's say semi-simple, and modulo conjugacy. And then the Durant space of x, which is the moduli space of flat vector bundle, so vector bundle with an integrable connection, holomorphic integrable connection. And finally, the Higgs space of x, which is the moduli space of Higgs bundle, like semi-stable Higgs bundles. And so here theta is a Higgs field, so it's an element of endomorphism of E tensored with omega 1 of x. So these are three moduli spaces, and they are, in fact, related to each other. There is so the classical Riemann-Hilbert's correspondence says that there is these two are biholomorphic. And, well, it results from the work of several people. Well, it started actually with Narasimhan and Seshadri, and then Donaldson, Yao, Uhlenbeck, Corlett, and then Simpson, that these two are also, in fact, they are homeomorphic. Namely, to any flat vector bundle, you can associate a Higgs bundle, and this correspondence goes through like the set of harmonic bundles. It's really a highly analytic statement, like involves like some construction of metrics, which is really like involves like some PDEs and solving like some. It's really highly transcendental. Now, the nice thing about the moduli space of Higgs bundles is there is an action of C star. Yeah. So these are yeah. Yeah, all up to isomorphism. So there is an action of C star on M Higgs, which is basically you take any complex number which is non-zero, and there is a way to construct a new Higgs bundle by making T act on the Higgs field theta. So this defines an algebraic action of C star on M Higgs. So I mean, all the three of these are algebraic varieties, but their algebraic structure are not compatible under these different isomorphisms. And there are like several conjectures that try to understand the nature of this homomorphism, like P equal W, or and today, so there's going to be a question about the interaction of these three moduli spaces. So this action of C star on M Higgs, now you can consider the fixed point under this C star action. And those Simpson identifies as what he calls the C-polarized variation of Hodge structure. So on the theorem side, these are just filtered vector bundles which satisfy the Griffith's transversality condition. And if furthermore you impose that I'm going to just, for simplicity, write something like this. If you intersect this with the set of representation of pi1 of x that land in GL and Z, so meaning I transform this under the non-abelian Hodge, non-abelian Hodge correspondence via this work of Simpson. So I have this locus lives here, and then I see it in MBT, and then I intersect it with the locus of representations which are integral. Then you recover exactly the set of Z PVHs. So these are the Z polarized variation of Hodge structure. So they have a Hodge filtration who satisfy Griffith's transversality, and they have integral monodromy. So there's a lattice. And in fact, Deligne's result is that this set is finite. So it's not really interesting in if you do this work for only one family. Now, if you take for only one variety, but now you can do it. You can do the same. You can do the same discussion for a family of smooth projective family of algebraic varieties. So now, if you fix X over S, smooth and projective, there are similarly three moduli spaces. There is MBT, X over S, and then M de Rham, and then M Higgs. And these three objects parameterize representation of fundamental groups of the fibers of the fibers of the family. This parameterizes flat vector bundles on the fibers of the family, and this parameterizes like semi-stable Higgs bundles on the fiber of the family. And so you have similarly an action of C star here on this M Higgs that you can. There's similarly a non-abelian Hodge correspondence that you can look at it inside MBT, and then the non-abelian Hodge locus is by definition the sets, so the representations of the fiber that lands in GL and Z intersected with, under this correspondence with the C star fixed point of M Higgs. And so these are the set of Z-polarized variation of Hodge structure on the fibers of the family. Okay, so Simpson proves that this is an analytic set. This is an analytic structure, which is not a priori clear because this is just a homeomorphism and doesn't respect the analytic structure. So there's something to say, some arguments to say, and like it has so this non-abelian Hodge locus seen inside MBT by this result of Deligne is the non-abelian Hodge locus is proper over S. And okay, so the main conjecture in this setting, which is due to Simpson, is that this non-abelian Hodge locus is algebraic, has an algebraic structure, and both the inclusion inside MBT and M Higgs are algebraic morphisms. So this implies actually the conjecture of, the question asked by Deligne, because representations that underlie a ZPVHS, because this locus is algebraic, it's going to have only finitely many connected components. And so representations of the fundamental group, like locally, like if you are along a connected component, then they're not going to change. And so it implies the finiteness of the monodromy representation, but it's much more stronger. Because once you fix the monodromy representation, you can ask, now what does the locus, yeah, let me. So once you fix a monodromy representation, you can ask what's the locus in S, where the deformations of this of this algebraic variety, and like you can deform the representation of pi1 to nearby fibers, and it still underlies a PVHS, and then you ask, is this still algebraic in the base? And that's what Simpson's conjecture is about. Okay, so you may ask why why formulate such conjecture? Well, first, it's the analog in usual Hodge theory is exactly the Deligne, well, the Cattani Deligne Kaplan theorem. Yeah. So in usual Hodge theory, this is exactly Cattani Deligne Kaplan, and which is known. And well, we all know that this Cattani Deligne Kaplan theorem is implied by the Hodge conjecture. And in fact, there's a similar, you can formulate a similar conjecture in the setting of non-abelian Hodge theory. And this is also a conjecture due to Simpson. But this one is even harder than the Hodge conjecture. So I don't even know what the price money should be. Any Z local system on a variety X that underlie a ZPVHS is motivic. So underlining a ZPVHS corresponds to saying that you are fixed under the C star action on M Higgs. And for Hodge classes, being a Hodge class means that you are in the middle part, but if you adopt like the point of view of the Deligne torus, that means that you are fixed under the C star action on the usual cohomology. So the analogy is perfect. I didn't say, I guess, what motivic means. This local system V itself might not be the cohomology of a family of algebraic varieties that live over X, but the statement is that there is some Zariski open subset U inside X, such that Vz is a factor of the Gauss-Manin system coming from from this family of algebraic varieties over U. So such that V0 restricted to U is a factor of this. So okay, so there's no need to restrict. Is a direct factor of. Sorry? Yeah, maybe let's say over Q. Yeah. Yeah, thanks. And so, of course, this let's call it this conjecture 2. And this is conjecture 1 by the similar type of arguments that are in Cattani, Deligne and Kaplan. Like 2 implies 1.
Why is 2 harder than the Hodge conjecture?
The what, sorry?
Why is 2 harder than the Hodge conjecture?
I mean, a large inequality. I don't say it's strictly harder, but it seems, it seems like,
They have no relation to each other.
no, they have no relation to each other, but it just seems like, I don't know, for me, it's like, just seems like, how do you start like a approach a statement like this?
On average, things are easier.
The what, sorry?
This is still a version on average. It's like on average, it's a fundamental group or so.
This is, so your x is fixed now. So and now you're asking to construct a family over x whose monodromy is, or like a Gauss-Manin system contains as a factor this one you started with. And so, there are some cases which are known, like analog to somehow Lefschetz theorem in Hodge theory, but in general, like nothing is known about this. As long as as I know, there's like no analytic approach or there's no paper like actually trying to prove it. Versus the Hodge conjecture, there's a lot of papers that try to prove it and failed, but here there's no paper that tried to prove it and failed. Yeah. It's a personal statement. I'm not saying this is. Maybe it's easy. I don't know. And one last comment is that, of course, as in Cattani, Deligne and Kaplan, when the base S is compact, then this is just Gaga's theorem, and there is actually nothing to prove. So this is also something that happens in usual Hodge theory. So when S is compact, then 1 is true. And this is basically just Gaga. Okay, any question on the setup? Okay, so now let me explain the results that we obtained with Philip. And for this, let me just make a definition. If you have a representation of the fundamental group of X inside GL and Z, so we say that rho has a Q anisotropic monodromy if the algebraic monodromy group, so let me call it H, so the Q algebraic monodromy group is Q anisotropic. So maybe a simpler way of saying that is that if you take the Z points of H and then the quotient HR mod HZ is compact. Yeah. Yeah, which one? Yeah.
For one Hodge structure, it's easy to construct that Z or structure that doesn't come from geometry, right?
So, yeah, exactly. That's in fact, there's a subtle point here. I'm not saying that the Z PVHS itself is motivic, but I'm saying the local system is motivic. So if you just take So it means that you take any lattice, then any lattice, you can put a Hodge structure on it that's come from geometry, and you just take a Hodge state Hodge structure or something. So that's, yeah, so that's like the subtlety about this theorem is that you can, yeah, of course you can find like Hodge structures that do not come from geometry, but then you forget about them, and the underlying lattice has a Hodge structure that comes from geometry. That's why it's,
Okay, here in this hypothetical geometric one, I tensor it with a isotrivial one as to a known thing, then you change it.
yeah, exactly. Okay, so theorem one. So this is with Deligne's question. Is true, or like has a positive answer. For representations, so for representations of the pi1 of x, or like any x in the family. So again, let's fix x in the family, and then, I mean, in fact, I can just, yeah, okay. For some pi1 of x at some point inside GL and Z with Q anisotropic monodromy. Okay, maybe for Q anisotropic monodromy. So that means if I'm only looking at ZPVHS that appears on some fiber of the family and which have Q anisotropic monodromy, then this, there are only finitely many of those that appear up to conjugacy and up to the mapping class group action from the base. And theorem 2 is Simpson's question, or like Simpson's conjecture, is true for, again, for the same type of object, for the representation of, so somehow in this non-abelian Hodge locus, I can look at the components which underlie, so I mean, an element here is like so a fiber and a representation of the pi1 of the fiber into GL and Z, and so I can restrict only to those that underlie PVHS, so I can, if I look only at those which are, which have Q anisotropic monodromy, then this locus is algebraic. So, yeah, so Q anisotropic monodromy is not is an assumption that, for example, is satisfied. Like you can find example of ZPVHS with Q anisotropic monodromy in all Shimura varieties, not only those of abelian type, but also the exceptional type. But it would be interesting to find some which are not of Shimura type. So this is something, an example. We don't have an example. If you do, let me know. But yeah, but the original strategy, we're actually trying to analyze the full situation, and the Q anisotropic monodromy just gave us a roadmap to approach these two questions. So let me explain the ideas of the proof. Are there any questions on the statements? No restrictions. Yeah. So if the base S is projective, then it follows easily from Simpson by Gaga. And so the only interesting case is when S is quasi-projective. Yeah? No, sorry. It would be interesting to find ZPVHS with Q anisotropic monodromy and that are not parameterized by Shimura variety. So for Shimura variety, it's very simple. Once you take a compact quotient of a Shimura variety, you can take any subvariety, and then that will give you an example for ZPVHS. In general, like even if you construct the compact quotients of Mumford-Tate domains, you have no guarantee that you can find subvarieties that are tangent to the Griffiths distribution, because it's not integrable. So you have. So you try to do with like surfaces, hypersurfaces, a lot of type of abelian variety, algebraic varieties, but we didn't really get any example. So yeah, so that's the question.
But your conditional on the monodromy is killing the monodromy at infinity. You're saying your VHS at infinity.
Yeah, so the VHS will extend to a compact, like by Griffith's properness, like automatically it will extend to a compactification of the base.
But then you said you know Simpson project on the compactification.
Oh, no, okay, so there are different compactifications. So, so this is the pi1 of a fiber of S, and Simpson is like when S itself is compact, so the family doesn't degenerate versus, yeah, so they're like, yeah, it's like a bit, so yeah, there's like a base family and then X that varies over the family, and then a ZP VHS that's come from our geometry would be a family over a fiber of this family.
And there's no link between this like fiber-wise monodromy and the base monodromy. There's some
Well, I mean, the pi1 of the fibers is a local system, and they're the pi1 of the base. So there's like, so the pi1, like for example, for the family of curves, the pi1 of the base would be just like the mapping class group acting on like up to some finite index on the, well, no, it's mapping class group on the pi1 of the fibers. So yeah, as far as I know, for example, there's no analysis similar to Schmidt or Griffiths of the degeneration theory of local systems on the fibers and link them to the pi1 of the base. So this would be interesting to do.
maybe there's something in the work of Morgan there's something called the non-abelian SL2.
The sorry, what?
The non-abelian version of the SL2 or the nilpotent orbital.
Yeah, they do have some, but nothing. Nothing that we actually used. So, okay. So, in the remaining time, let me give some ideas of the proof. So, so in fact, theorem 1 or question 1 can be reduced to family of curves. I mean, Deligne formulated for curves, but in fact, starting from any morphism, like you can always reduce it to curves, and so you can reduce it to the universal family of curves. In fact, because of this assumption on Q anisotropic monodromy, you can reduce it actually to the smooth projective family and not like punctured curve. So from now on, I will assume that my X over S is just this universal family of curves. And this MG has a decomposition in the following way. For any gamma in the surface group of a curve of genus G, and if you fix a curve C0, like a smooth projective curve of genus G, then the homotopy, the free homotopy class of gamma has a representative of minimal length. So if you imagine your Riemann surface is doing like this, so gamma has some representative of minimal length, which is a geodesic, and this is like, so this is the loop gamma, and so this length, let's call it L C0 gamma. So it depends, of course, on the complex structure on C0, or equivalently, it depends on the hyperbolic hyperbolic metric on C0, which varies when you vary over Mg. Now, Mg has a decomposition into two sets. That's so if you fix any epsilon positive, this Mg can be decomposed as let me for now say Mg bigger than epsilon, disjoint union with Mg less than epsilon. And this Mg here is the set of curves such that the length of any of any free homotopy class is at least epsilon. So, so the minimal length of any curve in this in mg bigger than epsilon is at least epsilon. So this L gamma here is bigger than epsilon. And then the other set, mg less than epsilon, is complementary. So this corresponds to Riemann surfaces where there is like a long neck that appears. And so like the core curve here has length less than epsilon. And so there is also a curve, like a geodesic, that goes through this color. And now the length here is, well, roughly 1 over epsilon. So these are the curves actually that approach the boundary of mg. So the way a Riemann surface degenerates is that there is some curve that forms and then that pinches to form a node. And geometrically, this is exactly what happens. So the next question could be analyzed into 2 sets. So in this set actually is relatively easy, and the treatment is exactly the one that Deligne did. So let me remind quickly how that goes. So if you have a curve in this mg bigger than epsilon, and so some representation of the pi1 of C0 at some point in GL and Z that underlie a ZPVHS. Then you get a period map, as we saw throughout the week, to D mod gamma, to some Maffertate domain modulo some group gamma. So let's call this period map phi and this rho. And so now you can take, if you take the universal cover, so this is the tilde that lifts to D. Actually, let me call this phi. I don't need the map here. So, and the phi here is rho equivariant. Now, an important property that has been observed by Griffiths is that with respect to the metrics, like the hyperbolic metric on C0 tilde and the GR invariant metric of D, phi is length contracting. Okay, so what this means is that if you take any element gamma in the pi1 of C0 and you compute the distance between, so let's fix a base point here and call it A and map it to, I don't know, B. Then the distance from rho of gamma acting on B and B is smaller than the distance from gamma acting on A and A. And now this only depends, this depends on the, on the homotopy class of gamma, and so this is bounded. Now, now the sets of matrices in GL and R, or like I say GR, for which the distance, like that move B to a bounded distance, in fact, this set is compact. This is basically saying that the projection from GR to D has compact fibers, and so it's furthermore, you move B by a bounded distance, then the set itself is bounded. So, so what this says is that all the rho gammas land in a compact set, so they have like bounded entries, but there's something here just subtle. It's just there are bounded entries in some orthonormal base associated to A. But you can still say that the trace of rho gamma, the consequence, is bounded. But this is also an integer. So it takes finite values. So the result is that, in fact, this this representation, this so by theorem of Procesi, this, well, and Deligne first. So Deligne says that rho is semi-simple. So it's completely determined by the trace of elements of the pi 1. So this determined completely rho. And then the theorem of Procesi tells you that, in fact, it's enough to consider a finite set of elements in sigma g that determine completely the traces of rho gamma for all gamma in sigma g. So in other words, it's enough to know the traces for a finite set of elements in sigma g to be able to know the traces of all elements in sigma g. And now the semi-simplicity tells you that if you know the traces of all elements, then you know the representation itself. But then this analysis says that the traces of rho gamma I are all in some interval of integers, so they take finitely many values. And this is how you get definiteness in this setting. Okay. Now, the harder part is to analyze what happens in when the curve degenerates. So when the curve degenerates, there's a problem here because this bound does not yield anything interesting because this distance from like the displacement by an element gamma could go to infinity for like this elements of the fundamental group that cross the color, and so they have a geodesic length that goes to infinity. So so here we still would like to prove that the trace of rho gamma acting on A, the trace of rho gamma is, or like rho gamma I for a set of Procesi generator is still bounded. And now the idea is to decompose, like take a decomposition of this Riemann surface into a pair of pants decomposition. And in particular, you will have some pieces of the Riemann surface that degenerate and the others that keep a bounded geometry. And like you can imagine if your loop gamma like crosses the color like this, then the length of gamma, or like the length of the geodesic representative of gamma goes to infinity. And so one way of handling this is like if you call this this piece here C gamma, so the crucial proposition is that if you just restrict to C gamma lifts to D, and this follows from the Q anisotropy assumption. And not only it lifts to D, but it arrives into some bounded set inside D. So bounded meaning as epsilon goes to 0. So then, okay, so this is like crucial because now if you have a path, let's say that loops around like this, and then that crosses the color, and then that loops along like this, and then maybe crosses again, and then come back, then each time you are outside this like part that shrinks, then you're fine because this would only like move the point by a bounded distance. And then this proposition tells you even like inside the color, it wouldn't move the point by a bounded distance. So the result is that in the matrix of rho gamma still has bounded entries, like by doing a careful analysis how this path loops around in the Pence decomposition. And again, so bounded entries in some bases, in some orthonormal bases corresponding to A, and so there's some base change you need to do to come back to Z, which may make the coefficients goes to infinity, but the trace doesn't change. So the trace is also bounded, and that's what you need. Okay, any questions on the? Okay, so now this first theorem actually is used as an input to analyze the conjecture of Simpson. So so let's come back now to Simpson's conjecture. So what this theorem says is that now if you start from x over s smooth projective morphism, then and you have some fiber, x is 0, and you have a representation of this pi1 of x is 0 into GL and Z, which satisfies that its monodromy is Q anisotropic. So we know that there are only finitely many such things that appear. So we can fix one and try to understand what's its deformation locus inside S. So what's the locus in S where xs, if you identify pi1 of xs to pi1 of x0, then this new representation still underlie a PVHS. And this can be analyzed actually via the period maps. So x0 has a period map to d mod gamma, so a holomorphic period map. And so deforming x0 to xs amount, or deforming the representation. So keep, yes. Oh, it's like in 2 minutes or no? Okay, 2 minutes. 1 minute. So deforming x0 to xs amounts, and I can keep in the representation and asking like that it underlies the PVHS amounts to a deformation of this period map to d mod gamma. So in fact, we are reduced to analyzing the space of maps from x over s to d mod gamma that are, let me call it, like Griffith's transverse. So parallel to the Griffiths distribution. And let me add the decoration here. So the map from the fibers of x over s to d mod gamma. And this is like the space we prove has an algebraic structure. So when d mod gamma is Shimura, this is like almost tautologic. And the hardest case is d mod gamma is not Shimura, because then in this case we know by results of Cattani, Griffiths, Strobel, other people that d mod gamma is not even a deformation type of Kähler manifold. So that's much harder. And a crucial ingredient is this space that we introduce, which is an analog of a Hilbert's Hilbert space. So there is a space that parameterizes all the subvarieties of d mod gamma that are that are tangent to Griffith's distribution. So d mod gamma is compact here by this assumption on Q anisotropic monodromy. And so this space here is parameterized by some Duadi space of cycles, which is a Moishizon space. So it's an algebraic space. Okay, so now using this space, you can see that instead of mapping to d mod gamma, you can map to the universal family over this Duadi space, and then there's some standard arguments in AG to conclude that this locus is algebraic. So you can see it basically as a projection of this algebraic space into S. Okay, let me stop here. Thanks.